So, Jamie, we have a broad portfolio, right, of activities. And this is just an example of some of the use cases under active development with our ecosystem partners. And you see here a broad set of categories. But one of the things that really comes to mind, in addition, at the bottom, for example, you see things for the financial sector, like risk and financial transaction settlement and so on. And one category that really comes front and center is this world of applying quantum computing to the world of chemistry, to the world of materials. And I'm inviting you to be on stage to share with the audience why is that so relevant and why is quantum going to impact that world?
All right. So, why? In 1981, 38 years ago, IBM and MIT co-hosted a conference on the physics of computation. And you may recognize some of these people. There's some pretty famous people in this photo, one of which is Richard Feynman. Feynman famously said at this conference, this quote, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy." And boy, is that true. So here's the idea. This is why chemistry, this is why we're interested in chemistry. So going from a design idea to something that can be commercialized, something that can be a product, is a multi-step process. A lot of the bottleneck comes down to making experimental observations and then having to explain them, which we use computer simulation for. There's a back and forth that goes between lab testing and computer simulation, and this can take months, years, and a ton of money to actually be able to figure out what's going on inside the flask before it can go on to scaling. In order to simplify this process, we've developed a number of different ways from a classical perspective to actually look at chemical systems. And they range the gamut between chemistry and materials and start falling over into the world of engineering. As we go to increasing length scales, so as we go from something on the atomistic level to something on the mesoscale, the accuracy decreases as you go across. And so what we've started looking at with quantum computers is quantum chemistry. So quantum chemistry is understanding the very most fundamental behavior of molecules on an atom scale. So this is essentially the bond-forming, bond-breaking reactions and describes how chemicals react. If we are to better understand this, we can then expand that to understand things like ground state properties, so different energies of the molecules, to be able to compare them to each other. That'll enable us to understand chemical reactivity, potential energy surfaces. We can understand properties of bulk materials, and then eventually be able to apply it to things like catalysis, which arguably impact all areas in chemistry. So why use quantum computers? So this is the basic concept. Classical algorithms to be able to accurately simulate a molecule scale exponentially in size. This means that every new atom that you put into the molecule, every new electron you put into the molecule, that math scales exponentially when it comes to modeling it on a quantum computer. This is essentially why we have to go to more approximate methods as we go across that plot that I showed you. However, quantum algorithms scale polynomially in size. This means that we can achieve highly accurate calculations and simulations for molecules while using much less compute. And that essentially means it will save time. And in that back and forth, time is money. And we've actually done this. So we've started looking at the dissociation profiles. That means when two atoms are pulled apart and the energies of the atoms of the system as you pull them apart from each other. We've been able to show that we can do this with an exact energy surface and then actually run it on our quantum hardware. And finally, chemistry applies to all sorts of different industries: agriculture, aerospace, transportation, pharmaceuticals, you name it. And you can think about the potential power to be able to harness quantum computing, to be able to use this towards looking at some of the world's biggest problems for industry, such as nitrogen fixation, new catalysts for CO2 conversion, high-performance polymers to lightweight airplanes, antibiotics, electronic materials, and electrolytes for potential next-generation batteries. And the list goes on.